Now we are going to continue with the second part of this lab, transfer learning and fine tuning. So to just basically overall give a brief description on the transfer learning is that sometimes we don't need to spend a large amount of time to train a model, because certain models, for example, let's talk about it here. We are in the domain of convolution or image processing. Let's say player A has developed a convolutional model over a large amount of data, and they have publicly released that model, so and everyone else can use that model. And what we know about convolutional models are that the early layers in convolutional models, as we saw in the previous lab, will focus on learning concepts like edges, shapes, I don't know, colors and stuff like that. So those learnings are kind of generalized across different domains. That means that if I have the concept of the colors over a data set that maybe was used over maybe a data set of animals, the same concept of color, maybe it's applicable to a data set of cars, because these concepts are the same thing. So the transfer learning basically says that instead of retraining a model, you can pick someone else's model and transfer the learning or the knowledge that that model has to your own model. Now, the idea of transfer learning basically it's that we just want to share the information to reduce the training time. That way, we also require less amount of data. It has a better generalization and is more resource efficient, basically, for us. Now, we're going to cover two types of transfer learning here. One is that feature extraction, and basically, feature extraction is that we have basically we have a pre-trained model, and what we do, a pre-trained model that has a certain layers, and especially in convolution, the last layer is fully connected. What we do, we remove that last layer from this pre-trained model. And so we keep all the layers intact except the last layer of this model, and we add some additional layers ourselves to this model. So in the concept of feature extraction, so we just remove the last layer, and let's say we add one new layer instead of the one that we removed, and we train the model. So that way, we are basically using the knowledge that the original model has without changing the weights and the parameters of that model. So when we train the new model, we do not update or backpropagate through the pre-trained model. We only backpropagate through the only layers that for example, we have added to the model. So that's going to be a feature extraction, and then we have fine-tuning. The idea in fine-tuning is that similar concept, but this time instead of just removing a layer and don't train anything in that model, we actually basically bring a pre-trained model and we add some additional layers to it. Or even if we don't add any additional layer, we basically, let's say we have the same types of data, same number of dimension, we might actually just, what we do is that we just unfreeze certain number of layers from this model, and we train those layers. So let's say we have there is a model that has 100 layers. What we will do is that we keep first 60 layers of this model frozen, so we don't train on those, and the last 40 layers we basically will train. So that way, basically, we are still keeping a large amount of knowledge from the pre-trained model, which saves us lots of time, but we also fine-tune the last 40 layers of this model to the domain that we are interested and we are working on. So that's called also fine-tuning. Now, in order to do that, so in this example, we're going to work with any of these models like a VG16 or 19, ResNet 50, Inception models, MobileNet, EfficientNet. Those are some popular pre-trained basically vision models. So all we do, we basically set up the environment. We load some basically data. There's some things for pre-processing the data, similar to other labs that we have seen. And then this is the part we are going to do the feature extraction. So in this function create model, first thing is that we load the MobileNet version 2, and the weights are coming from ImageNet. Here there is a parameter that says include top, and I set that to false. What does that mean? So if you think about a convolution, the last layer of the convolution is that fully connected. So if you set this to true, it also will bring that last layer. If you set it to false, it brings every layer except for the last one. So that means if the model had pre-trained models, MobileNet, for example, has 100 layers, we are basically loading 99 layer and we drop the last one layer. So that's, we call this a base model. And we are basically saying that base model.trainable, and we set that to trainable here is false. That means we are basically saying that this model is not trainable. We are not going to update anything about this model. Then we create our own model, and our model, basically the way that it works, we at the beginning we have the base model. So that means the first layers of our model is this base model. Then we add additional couple of layers to it. That's totally up to you how many layers you're adding. I just add a global, average pooling, a dropout, and a dense layer. And it's a classification, number of classes, and softmax. So this becomes our model. So if we run this, basically, now this is our model. As you can see, our model has the first layer of our model itself is a functional model, as it says here, MobileNet. That model has 2,257,000 parameters. Then we added 3 layers to the end of that. Okay, we can also get the summary of those, some details from those models. So if I say initial model that layers, so if we pick that and we say that summary, so this is the MobileNet, and as you can see, this is a really long and large model. So that's the reason. So someone else, think about this idea that someone else has trained this model and is publicly available for you to use. So I highly recommend that when I say publicly available, to read the disclaimer to be sure that if it's actually available for the task that you are basically trying to do. But so what we do is we don't need to train anything like this. This already has been trained. All the weights are frozen, and we just simply use that by basically creating a model which has 3 layers that we only going to train. So we are going to only train these layers instead of all of it. And basically in this part, we also introduce an earlier stopping. We also introduce another callbacks called reduce learning rate on plateau. And that means that if the model basically detects that it has stuck in some plateau, it has plateau, basically the learning, so basically it reduces the learning rate. So it makes it, the learning rate smaller. Then we have this model checkpoint to basically keep track of the checkpoints and saves the checkpoints in case the model basically is stopped or something breaks. So we have the checkpoint. You don't need to redo the training. You can continue from the place that it was basically stopped or broke. So you can run that. And I already run it. It takes actually quite a while, because the amount of data also go over. So there's an error here. So let's close that. So I'm not going to run this, but this also what you could do is that you can basically, after running this, you can do the same thing and get the abstract representation of the data from, or the activations map, from the model that you have and from the MobileNet version. So the next one is the fine tuning, and the difference here in the fine tuning is that basically we said that instead of just add additional layers, what we will do in fine tuning is that we create a model, we add some layers to it, but from the MobileNet model, we are also going to train the last 40 layers. So here, basically, the last 40. So here, I basically say that from layer 0 to 40 to the last, we set those to trainable to false. That means we are not going to update those, but the last 40 layers, basically, we will update. And then you perform the same thing. You basically train the model. This time it even becomes basically slower, because now what we are doing, we also update the last 40 layers from the MobileNet. And this is basically what it calls fine tuning here. And then you basically apply the data, and so here also we get some visualization. So as you can see, for example, on the first row top, this is the result from feature extraction, the first technique that we use. And as you can see, there is a gap between training and validation. So accuracy and training is lower than the accuracy and validation, the loss also, which is kind of some ideas of like basically underfitting here, like we are not learning properly. And the bottom one, which is the fine tuning, and as you can see, basically the gap basically is reduced now. So we basically improve the learning by doing the fine tuning. It's more expensive to fine tune, but still, it gives us a better performance. All right. So I will leave the rest again for everyone to try out. And we will have further labs that will come in the other part